Hello everyone. So one last example. We're going to work through a related samples hypothesis test. So here we go. Suppose you wish to test the effect of Prozac on the well-being of depressed individuals using a standardized well-being scale that sums Likert type items to obtain a score that could range from 0 to 20. Higher scores indicated greater well-being. That is, Prozac is having a positive effect. Do the data indicate Prozac has a positive effect on or increases well-being scores? So here's the table. Well-being pre-Prozac, right? So before taking Prozac, here are the well-being scores. And then we give our sample of individuals the Prozac, and then we take a post-Prozac well-being scores, right? So we've tested these individuals twice. So this is how we know this is a related samples design, because we have 2 scores per individual, right? So this is participant 1, participant 2, participant 3, 4, 5, 6, 7, 8, and 9. So there are not a total of 9 participants who have 2 scores each. Okay? So we're going to conduct the appropriate hypothesis test using alpha equal to 0.05. We're going to state our conclusion in terms of the problem and then make sure to use APA-style conclusions. So, because we're dealing with raw data, we're going to have to start from scratch. We're going to have to calculate the sample mean and the sample standard deviation to start with, right? So the first thing we're going to have to do, because this is a related samples design, is we have to calculate the difference scores. And remember that difference scores are x2, so x2 minus x1. So I went ahead and added a column right here, right, that has the difference scores. And I've already calculated these. So for subject 1, the difference score is 2, and then 0, 1, 1, 2, 2, 4, 3, and 3. So you can see here how I calculated this score. Okay? And of course, in order for us to do sample standard deviation, we're going to have to also square all those difference scores. So I went ahead and squared them here. So let's go ahead and take a look. I want to make sure we can still see the table. All right, so our sample mean, when we add these difference scores, so it's 2, 3, 4, 6, 8, 12, 15, 18, right? So the sum of the difference scores is 18, n is equal to 9 because there are 9 difference scores. So our mean of the difference scores is equal to 2. Right? Our sample standard deviation, we're going to do the same thing we've done way back at the beginning of the intercession, right? This formula should look somewhat familiar. We've only replaced x's with different scores, right? So I went ahead and added these, and this is equal to 48, right? And then 18 squared, right, is equal to 324, right? So 48 minus 324 divided by 9, all divided by degrees of freedom, which is n minus 1. 48 minus 36 divided by 8 gives us 12 divided by 8, which gives us a sample standard deviation of 1.5. All right. So step 1, state our hypotheses. So our null hypothesis, right, it's a one-tailed test. This is a one-tailed test because we're looking at whether or not Prozac increases well-being, right? So our mean of the different scores for the null hypothesis, we're going to say that it doesn't increase well-being, so its mean of the different scores less than or equal to 0. So Prozac does not increase well-being scores. The alternative is that the mean of the different scores is going to be greater than 0. So Prozac increases well-being scores. Step 2 is to set the criteria and locate the critical region. Alpha is 0.05. It's a one-tailed test. The reason why we know it is, remember, the question asks whether we have a positive effect or whether Prozac increases. So now we're actually working on the right side of the distribution, right? So we're going to get positive values. So degrees of freedom is n minus 1. 9 minus 1 is equal to 8. Our T critical value we need to look up on our table. So let me pull that up real quick. Okay, so we're looking in the one tail, 0.05, right here. So this column. And our degrees of freedom are 8. So we're going to go to the row where it says 8, which is right here, degrees of freedom 8. Move over to 0.05 with a one tail. So our T critical value is 1.860. So this is the value we need to beat. Our calculated T, or our obtained T, has to be larger than 1.86. Step 3 is to calculate the test statistic. This is going to be just like our one sample t-test, right? So here's the t-test formula. So the mean of the different scores divided by estimated standard error. And estimated standard error is our sample standard deviation divided by the square root of n. This is supposed to be a small n. Let me change that real quick. There we go. All right. So first thing, I always like to do estimated standard error first so that I don't have a fraction inside of a fraction. So our estimated standard error, right, is sample standard deviation, which was 1.5, divided by n, which is 9, or divided by the square root of n, which is the square root of 9. So 1.5 divided by 3 is equal to 0.5. That brings us to the formula. We just plug everything in. The mean was 2. Our estimated standard error is 0.5. So our calculated T, or our obtained T, is equal to 4. Step 4 is to make a decision. Our obtained T is equal to 4, which is greater than our T critical value, which was 1.86. So our decision is to reject the null hypothesis. And since we're rejecting the null, we need to make sure we calculate an effect size. So I'm doing R squared, right? So T squared divided by T squared plus degrees of freedom. Remember that it's the T observed, right? It's the obtained T. So it's 4 squared divided by 4 squared plus 10. 16 divided by 16 plus 10, which is 16 divided by 26, which is equal to 0.615. What this means, and I don't think I've explained the interpretation. The interpretation of R squared is basically that approximately 62% of the variability in the dependent variable is caused by the independent variable. So 62%, let me make sure that I said this correctly. 62% of the variability in our dependent variable is due to or caused by our independent variable, right? So approximately 62% of variability in well-being scores is caused by taking Prozac. That's what this means, all right? And by the way, this is a very large effect. 95% confidence interval, mean of the different scores plus or minus our margin of error, which is T critical times estimated standard error. So 2 plus or minus 1.86 times 0.5 is equal to 2 plus or minus 0.93, which gives us a confidence interval of, there we go, forgot to put the bracket in there, 1.1 to 2.9. So our conclusion Reject the null. There is sufficient evidence to conclude that Prozac significantly increases well-being scores. T with degrees of freedom of 8 is equal to 4. P less than 0.05. R squared equal to 0.62, which is a very large effect. Our 95% confidence interval, 1.1 to 2.9. Prozac has a positive effect on the well-being of depressed individuals. And there we go. We just did a related samples example. This was much easier, right?